Welcome to my YouTube channel. I'm SV SUBANU, currently pursuing BA Computer Science in SHREE.S.V Institute of Technology. I have been given a topic Hadoop in Big Data to create a seminar video. Let us get into the topic. From this video, you will come to know about what is big data, applications of big data, what is Hadoop, subprojects of Hadoop, Hadoop architecture, topology in Hadoop, features of Hadoop. Now, let us see what is big data. The big data is the collection of data that is huge in volume, yet growing exponentially with the time. It is the data with so large size and complexity that none of the traditional data management tools can store it or process it efficiently. The big data is also a data but with huge size. The following are some of the applied areas of big data: banking and securities, communication, media and entertainment, healthcare providers, education, manufacturing and natural resources, government and insurance. Now, what is Hadoop? Apache Hadoop is an open source software framework used to develop a data processing application which are executed in a distributed computing environment. The application built using Hadoop or run on a large data set distributed across a cluster of commodity computers. The commodity computers are cheap and widely available. They are mainly useful for achieving a greater computational power at low cost. In Hadoop, the data resides in a distributed file system, which is called Hadoop Distributed File System. The process of model is based on a data locality concept, wherein a computational logic is to cluster nodes containing data. This computational logic is nothing but a compiled version of a program written in a high-level language such as Java. Such a program processes data stored in Hadoop. Apache Hadoop consists of two subprojects: Hadoop MapReduce, Hadoop Distributed File System. Hadoop MapReduce. The MapReduce is a computational model and a software framework for writing applications which are run on Hadoop. These MapReduce programs are capable of processing enormous data in parallel on large clusters of computational nodes. Hadoop Distributed File System. The Hadoop takes care of an storage part of the Hadoop application. The MapReduce application consumes data from HDFS. The HDFS creates multiple replicants of the data blocks and distributes them on compute node in the cluster. This distribution enables a replicable and extreme rapid computation. Hadoop architecture. As we all know, a Hadoop is a framework written in Java that utilizes a large cluster of commodity hardware to maintain and store big size of data. Hadoop works on MapReduce programming algorithm that was introduced by Google. Today, lots of big brand companies are using Hadoop in their organization to deal with big data. Example: Facebook, Yahoo, Netflix, eBay, etc. The Hadoop architecture mainly consists of four components: MapReduce, Hadoop Distributed File System, yet another resource negotiator, common utilities, or Hadoop Common. MapReduce is mainly used for a distributed processing, whereas the Hadoop Distributed File System is used for a distributed storage. A YARN, yet another resource negotiator, is used for job scheduling and a resource manager. Hadoop Common consists of an library functions and utilities. Let us understand the role of each one of this component in detail. MapReduce. The MapReduce is nothing but is just like an algorithm or the data structure that is based on a YARN framework. The major features of MapReduce is to perform a distributed processing in parallel in a Hadoop cluster, which makes Hadoop working so fast. when it comes to an big data, the serial processing is no more of any use. The MapReduce is mainly of two tasks, which is divided into pace-wise. The first pace is utilized by the map and the next pace is utilized by the reduce. Here we can see that the input is provided to the map function, then its output is used as an input to the reduce function, and after that we receive our final output. Let us understand what is map and reduce function does. As we can see that the input is provided to the map function. Now as we are using big data, the input is a set of data. The map function here breaks their data blocks into tuples that are nothing but a key value pair. These key value pair are now sent as an input to the reduce. The reduce function then combines the broken tuples or key value pairs based on their key value and form of set of tuples, and perform some operations like sorting, etc., which is then sent to the final output node. The final output is obtained. The data processing is always done in the reducer depending upon the business requirements of the industry. This is how first map function and then reduce function is utilized one by one. Let us understand the map task and the reduce task in detail. Map task. The record reader. The purpose of the record reader is to break the record. It is responsible for providing the key value pair in map function. The key is actually its locational information and value is the data associated with it. Map. The map is nothing but a user-defined function whose work is to process the tuples obtained from the record reader. The map function either does not generate any key value pair or generate multiple pairs of these tuples. Combiner. The combiner is used for grouping the data in a map workflow. It is similar to the local reducer. The intermediate key value that are generated in the map is combined with the help of this compiler. Using the compiler is not necessary as it optional. Partitionary. The partitioner is responsible for fetching the key value pair generated in the mapper pace. The partitioner generates the shades corresponding to each reducer. The hash code of the each key is also fetched by the partition. Then the partitioner performs its modules with the number of reducer task. The shuffle and sort. The task of the reducer starts with this step. The process in which the mapper generates the intermediate key value and transforms them to the reducer task is known as shuffling. Using shuffling process, the system can sort the data using its key value. Once some of the mapping tasks are done, the shuffling begins. That it is why faster process and does not wait for the completion of the task performed by the mapper. Reduce. The main function or the task of the reduce is to gather the tuple generated by the map and then perform some sorting and aggregation sort of process on those key value pair depending on its key element. Out format. Once all the operations are performed, the key value pair are written into the file with the help of the record reader. Each record in the new file and the key and the value in the space separated manner. HDFS, Hadoop Distributed File System, is utilized for a storage permission. It is mainly designed for working commodity hardware devices working on a distributed file system. The HDFS is designed in such a way that it believes more in storing the data in a large bunks of blocks rather than storing a small data blocks. The HDFS in Hadoop provides a fault tolerance and high availability to the storage layer and then other devices present in the Hadoop clusters. The data storage nodes in HDFS are name node which will act as a master node and the data node which will act as a slave node. Name node. The name node works as the master in the Hadoop cluster that guides the data node. The name node is only used for storing the metadata, that is, the data about the data. The metadata can be a transaction log that keeps a track of the user's activity in a Hadoop cluster. Data node. The data nodes works as the slave data nodes are mainly utilized for storing the data in the Hadoop cluster. The number of data nodes are been from 1 to 100 or even more than that. The more number of data nodes, the Hadoop cluster will able to store a more data. So it is advised that the data node should have a high storage capacity to store its large number of file blocks. The high-level architecture of the Hadoop. Here is an example that how an name node and a data node will work. File blocks in HDFS. The data in HDFS is always stored in the terms of the block. So the single block of the data is divided into multiple blocks of size 128 MB, which is default, and we can also change it manually. Let us understand this concept of breaking down of files in block with the example. Suppose you have uploaded a file of 400 MB to your HDFS. Then what happens in this file got divided into a block of 128 MB, 128 MB, 128 MB and 16 MB is equal to 400 MB size. Means 4 blocks are created each of 120 MB. Expect the last one. The Hadoop does not know or it does not care about what the data is stored in these blocks. So it considers the final blocks or partial record as it does not have any idea regarding it. The Linux file system, the size of the file block is about 4 KB, which is very much less than the default size of the file block in the Hadoop file system. The read operation in HDFS. The read and write operation in HDFS operates at block level. The data files in HDFS are broken down into block-sized chunks which are stored as an independent unit. The read operation in HDFS. The data read request is served as a HDFS name node and data node. Let us call the reader as a client. The diagram represents the file read operation in Hadoop. A client initiates the read request by calling an open method of the file system object. It is an object of the type distributed file system. This object connects to the name node using an RPC and gets a metadata information such as the location of the block of the file. Please note that these addresses are the first few blocks of the file. In the response of this metadata request, the address of the data nodes have a copy of the block is returned back. Once the data address of the data node are received, an object of this type, FSDS, data input stream is returned to the client. The FS data input stream contains the DF input stream which takes care of an interaction with the data node and the name node. In step 4, as shown in the diagram, a client involves a read method which causes the DF input stream to establish a connection with the first data node with the first block of the file. The data is read in the form of stream wherein the client involves the read method repeatedly. This process of read operation continues till it reaches the end of the block. Once the end of the block is reached, the DF input stream closes the connection and moves on to the locate the next data node for the block. Once the client has done with the reading, it calls the close method. Now let us discuss about the write operation in HDFS. In this session, a client initiates a write operation by calling an create method of a distributed file system object, which creates a new file. In step number 1 in the above diagram, the distributed file system object connects to the name node using RPC call and initiates the new file creation. However, this file creates the operation does not associate any blocks with the file. It is a responsibility of the name node to verify that the file does not exist or already exist, and the client has a correct permission to create a new file. If the file already exists or the client file does not have a sufficient permission to create a new file, then the IO exception is thrown to the client. Otherwise, the operation succeeds and a new record of this file is created by the name node. Once the new record in the name node is created, an object of the type FDSS output stream is returned to the client. A client uses it to write the data in the HDFS. The data write method is invoked as shown in the step 3 in a diagram. The FS data output stream contains the DF output stream objects which look after a communication with the data nodes and the name node. While the client continues writing data, the DF output stream continues creating a packets with this data. These packets are enqueued in a queue which is called a data queue. There is a no more component called a data streamer which consumes this data queue. The data streamer also makes the name node for the allocation of the new blocks, thereby picking a desirable data nodes to be used for the replication. The data streamer pours the packets into the first data node in the pipeline. Every data node in the pipeline stores a packet received by it and forward the same to the second data node in the pipeline. The another queue, ACK queue, is maintained by the DF output stream to store the packets which are waiting for the acknowledgements from the data node. Once the acknowledgement for the packet in the queue is received from all the data nodes in the pipeline, it is removed from the ACK queue. In the event of any data node failure, the packet from this queue are used to reinstate the operation. Once the final acknowledgement is received, the name node is contacted to tell it that the file write operation is complete. Now we are going to discuss about the yarn process, the yet another resource negotiator. The yarn is a framework on which the MapReduce works. The yarn performs two operations that are job scheduling and resource management. The purpose of the job scheduler is to divide the big task into small jobs so that each job can be assigned to the various slaves in the Hadoop cluster and the processing can be maximized. The job scheduler also keeps track of which a job is important, which job has quicker priority, dependencies between these jobs and all the other informations like job timing, etc. And the use of the resource manager is to manage all the resources that are made available for running a Hadoop cluster. The features of yarn: multi-tendency, scalability, cluster utilization, and compactability. The Hadoop common or a common utilities. The Hadoop common or a common utilities are nothing but our Java libraries and Java files, or we can say that the JavaScript that we need for all other components present in the Hadoop cluster. These utilities are used by a HDFS yarn MapReduce for running the cluster. The Hadoop common verifies the hardware failures in the Hadoop cluster as common, so it needs to be solved automatically in software by Hadoop framework. Network topology in Hadoop. The topology of the network affects the performance of the Hadoop cluster. When the size of the Hadoop cluster grows, in addition to the performance, one also need to care about the high availability and the handling of the failure. In order to achieve this, Hadoop, the cluster information makes use of the network topology. Typically, a network bandwidth is an important factor to consider while forming any network. However, measuring a bandwidth could be difficult in this tree is considered as an important factor in the formation of the Hadoop cluster. Here, the distance between the two nodes is equal to the sum of their distance to their closest common ancestor. The Hadoop cluster consists of the data centers that tracks and the node which actually executes the job. Here the data centers consist of the rack and the rack consists of the nodes. The network bandwidth available to process various depending upon the location of the process. That is, the bandwidth available becomes lesser as we go from process on the same node, different nodes on the same rack, nodes on different rack of the same data center, nodes in a different data centers. Finally, we came to an end of our seminar. That is the features of the Hadoop. The features of the Hadoops are open source, highly scalable clusters, fault tolerance is available, high availability is provided, cost effective. Hadoop provides flexibility and easy to use. Thank you.